Okay, so let's start our last discussion. Yes. I have prepared some problems which are taken from probably CSR net. So problem number 1. Here we need to find what is the trace of that matrix A and B. So it is given that AB is minus BA and AB both are invertible. So from here, what can be done? AB is same as minus BA. Therefore,
Same invertible, so B is equal to minus B A inverse.
yes,
So it will be B is equal to minus B. So this will imply trace B is 0.
yes. No, B is not equal to minus B will not get because AB may not commute. But we are getting B is same as A inverse minus BA. From here, it is clear that B and minus B are similar matrices.
Yes sir, correct.
So, similar matrix has a nice property, that is, if
Trace are similar, same,
yes,
equal.
so if X and Y are similar, like this, P inverse Y P, then we know X and Y both have same eigenvalue. Because X and Y similar means those two will represent same linear transformation with respect to some different basis. We can easily check those two have same eigenvalue.
Yes sir.
Let me verify that fact. So suppose X has some eigenvalue lambda, that means X times some V is same as lambda V for some V non-zero. There exists V non-zero for which this holds, right? X has eigenvalue lambda. Then what can be done? We want to prove that being lambda is also eigenvalue of P, or maybe we can see that see the fact that determinant of X minus lambda is 0, right? That will imply determinant of P inverse X minus lambda P is also 0.
Yes sir.
Right? Because determinant is multiplicative. The date of A times B, is it same? Determinant of A times B?
Determinant A, determinant B.
Yes, it is product of determinant. Determinant
Yes.
is multiplicative. Therefore, from here it is clear, because date P inverse and date P will cancel each other. So, both are same. Now, determinant of this is equal to 0. That will imply determinant of P inverse XP, and now again P inverse P will cancel, so this minus lambda is 0. Therefore, P inverse XP has the eigenvalue lambda, right? So B and B minus B will be similar. From here, we can conclude that B and minus B has same eigenvalue. So
Yes.
suppose suppose B has the eigenvalue lambda 1 up to lambda n. Lambda 1 up to lambda n are eigenvalue of P. Then by similarity, lambda 1 up to lambda n, those are also eigenvalue of minus B. Because minus B and B are similar. Therefore, from here we can conclude. But we also note that
Sir,
yes.
first you solve this, then I will tell you.
Okay. So we also see that minus B has eigenvalues minus lambda 1 up to minus lambda n. It is easy to see, right? Bx equal to lambda x, maybe bv equal to lambda v. That will imply b times minus v, sorry, minus b times v is same as minus lambda times v.
Yes.
So from here it is clear that minus v has eigenvalues minus lambda 1 up to minus lambda n. So both of these set are same.
Yes.
From here we can clearly say this is
Lambda 1 is 0, lambda 2 is 0, lambda n are all 0.
yes, because lambda 1 this eigenvalue correspond to this same eigenvector. Lambda 1 and minus lambda 1 both correspond to same eigenvector. But with respect to given eigenvector, eigenvalue is unique, right? That is bv equal to lambda v means
No, sir, B and minus B are similar. So, sir, spectrum should be, sir, equal. Same, sir.
yes, but it may happen that this maybe,
Yes, sir, it
for
may
example,
correspond to something
this
other.
type of thing can happen, right? Minus 1 comma 1,
Mm.
suppose this is the eigenvalue of b, then those two set are getting same, right? But we cannot conclude from here.
Correct.
But the interesting fact is that with respect to given vector, given eigenvector v, so I am saying that if lambda and lambda dash two are distinct eigenvalue, those two are distinct eigenvalue, that will imply v and v dash are linearly independent.
Yes, sir.
Eigenvalue with respect to lambda and eigenvalue with respect to different lambda dash, those cannot be same.
Yes, sir.
Right. So from here it is clear if v is eigen, so corresponding to v we are getting that lambda 1 is eigenvalue of minus v, and corresponding to same v we are getting minus lambda 1 is also eigenvalue of same minus v.
Both are same.
Therefore lambda 1 and minus lambda 1 must be same. Therefore we are getting lambda 1 is same as minus lambda 1. Hence lambda 1 is 0. By the same property, we are getting all other lambda 2 up to lambda n. All those things are 0. So it is clear that what is trace? Trace of B is sum of eigenvalues, right? And we are getting lambda I, all lambda is are 0, therefore their sum is 0. So trace of B is 0. Trace B is 0, and similarly we can check trace of A is also 0.
Sir, if we take trace B, so from second equation,
Yeah.
if trace B is equal to minus time trace A inverse BA, sir. If we take trace of both sides, then it will be trace B is equal to trace of minus A inverse BA, sir.
Yes. Yes.
And we know that trace of ABC is equal to trace of BCA. We can write it, sir, BAA inverse.
Yes.
So A inverse will, sir, identity. So we will get, sir, minus trace B only. So trace B is equal to minus trace B. So this will imply trace B 0.
Yes, that is a better argument. We may write like this: trace of B is same as sum of those lambda I, but we are getting those two set are same, I equal to 1 to n. That is same as sum of lambda I minus lambda I, because those two set are same. So something is, but this is same as minus trace B, right? Therefore, 2 times trace B is 0, hence trace B is 0.
Yes.
Yes, that is a better argument. Easier to see. Okay. Similarly, we can check the same reason can be applied for A, and
A.
we will get trace of A is also 0.
Yes.
Okay. Okay. Yes. Maybe my earlier argument is wrong, because corresponding to that V, the problem is that P inverse AP times that V may not give. So I was saying that, um, sorry. So
Sir, if lambda and lambda dash are distinct, then V and V these are
so
linearly.
yeah, AV equal to lambda V, that will imply P inverse AP times P inverse V is same as lambda P inverse V. So that V we may not get same V. That is, same eigenvector may not work for the another similar matrix. Though eigenvalues are same, but same
Yes, sir.
eigen.
Eigenvector may not be same.
So the earlier argument cannot be applied. Sorry about that. So
Yes.
all eigenvalues may not be zero. That that argument is not working, but it may happen. Somehow one can prove.
Yes, sir. Yes, sir. They
Okay,
may
what
not be
about
zero.
yeah? So this may not happen. I don't know if this will be true or not. Okay, so
Sir,
let us.
actually, you are saying that if two matrices are similar, then
Yes,
yes,
though they have same eigenvalues, but corresponding to those eigenvalues, two matrices may have different eigenvectors.
correct. Yes.
So question number 2. So here Jordan canonical form is already given. We need to see which of the followings will have this Jordan canonical form J. Okay. So it is clear that
D is not, sir, the canonical form because
yes,
rank is not same.
yes. So what is the minimal polynomial of this J?
X is X square, I think, sir.
Yes. Clearly J is not 0. All eigenvalues are 0. So characteristic polynomial of this J will be x cube, right? X minus 0 whole cube, which is x cube. And what is minimal polynomial of J?
X
MJ?
square. X square or
Yes,
X.
because J is non-zero, but we are getting J square is 0. So the
Yes.
lowest and minimal polynomial also divides chi, characteristic
Sir, I
polynomial.
think J square is 0 or not
Yes,
0.
J square is 0 because 1
Mm,
0 0 first row is 0, first column is 0.
uh,
So J times J is 0. Okay. So from here, what can be said? That is, it is clear that uh, so
there is a Jordan block of 2 cross 2.
yes. Now, if
Is
we
equal
see
to
this matrix, then Jordan canonical form corresponding to this matrix, again, characteristic polynomial is x cube and minimal polynomial is x square, because first row is 0, so this times this will be 0. So minimal polynomial of this matrix is also 0. Mx is x square and chi x is 0. Chi x is x square. So from here, this data Jordan canonical form, what will be the Jordan canonical form? So all eigenvalues are 0, so we can put those things in diagonal. But now we can see that degree of uh, degree of mx, that is corresponding to the eigenvalue 0, x minus 0 whole square is appearing in minimal polynomial. That is, multiplicity of 0 is 2. Therefore, size of the largest block will be 2.
yes, sir.
So this is the Jordan canonical form. So Jordan canonical form of A is J. So A is one of the answer. Now what about this? The same thing can be done. We can easily check that though this
It's
matrix,
X cube, I think.
yes, though A is not 0, A square is 0, because sum of the first two column is 0. If you multiply 2 times, first two column will become 0, but the third column is sum of those first two column, which is again 0. So A square is 0. Therefore, again, the same thing can be done.
Sir,
That is,
sir, sum up. first two columns, how, sir? I am not understanding,
Yes.
sir.
So let me calculate this a square,
No,
right?
no, sir. Calculation, I clear, sir. Calculation is clear, but how are you, sir, concluding this without calculation?
Yes. So, uh, so ABC, if there is some ABC, then what is the multiplication? So let us see a 2 cross 2 multiplication. So suppose this is A1, A2, A3, A4, and B1, B2, B3, B4. Okay. So if you multiply this, or maybe let us consider this matrix only. This part it will be easy to see. If you multiply this is same as saying taking linear combination of this one. B1 times the first column plus B2 times second column. Okay. So that's why if you multiply twice, that is again 0, 0, 0, 0, 0, 0, 1, 1, 0. The first column means zero linear combination of these three columns. And what will be the second column? So zero linear combination means 0, 0, 0. So second column it contains 0, 0, 0. So if you take zero linear combination, 0 times the first column, 0 times the second column, 0 times the third column, it will become 0, 0, 0. Now what about third column? Third column is 1, 1, 0. So we take the linear combination will be like this: multiply 1 with the first column, multiply 1 with the second column, multiply 0 with the third column, which will give me 0, 0, 0. Because 1 times 0 is 0, 1 times 0 is 0. Therefore, their sum, this combination is 0.
Yes, sir.
So that is the interesting thing. That is, multiplying with column means it is linear combination of those columns.
Then with entries of the second matrix, columns,
Yes,
entries in the columns of the second matrix times the columns of the matrix A.
yes. Multiplying with some column vector, it means taking linear combination of the earlier matrix,
Yes, sir.
earlier columns. Okay, so from here we are getting the exactly same thing. That is, characteristic polynomial is x cube, minimal polynomial is x square. Therefore, all eigenvalues are 0, and mx is x square. Minimal polynomial x square means the largest size block is 2 by 2. Therefore, we will get the same Jordan form. So this is also true. Now, what about the last one? So again, the same thing. If you multiply twice, you will get 0, because first column is 0, and again first column multiplying twice will give you the first column of those two things. So it will become 0, it will become 0. So
Yes.
mx is again minimal polynomial is x square. So
Yes.
we'll get the same exactly same answer. Now what about the last one?
So rank is not same, so not, sir.
Yeah,
Cannot be the answer.
yeah. You can also check that rank of this matrix is actually 2,
Yes, sir.
but similarity preserve rank, right? So P inverse A times P cannot be 0, because similarity will preserve rank.
Yes,
So
sir.
rank of this matrix is 2, but rank of this matrix is 1. So this is definitely false. And you can see that rank of the earlier matrix are 1. Okay. So D is false, since similarity preserve rank. Since similarity preserve rank. And this is because of the fact that largest Jordan block, size of the largest Jordan block is same as degree, that is multiplicity of lambda in minimal polynomial. Minimal polynomial. Okay, corresponding to lambda. Now, what about this e to the power b? We need to find e to the power b. What is b? Okay, e to the power b is defined in this way. We need to find exponential of this matrix. And
characteristic polynomial of B.
yes, so p is characteristic polynomial which
E to the power P will be 0. So E to P be 0, sir. So E to the power 0 will be identity.
yes. So Cayley Hamilton say that every matrix satisfy its characteristic polynomial. That's why PB is zero matrix. Okay. Now PB is zero matrix means e to the power 0 means by definition this is same as 0 to the power some j by j factorial. J equal to 0 to infinity. But whatever power you choose, you will get 0. So it is the infinite series, but everything is 0. Therefore, this is 0. Sorry, e to the power 0, is it 0? 0. No, first one is 0 to the power 0. First one is non-zero actually. Means, let me write the whole thing, then it is clear. I am doing something wrong. E to the power b, it is defined if we write explicitly, first one is b to the power 0 by 0 factorial, which is defined as I. Then second one is b by 1 factorial, b square by 2 factorial, b cube by 3 factorial, etc. Therefore, first one is I, but if we put the value of b,
Yes, sir. Will become 0. Value of P of B.
yeah, it is e to the power pb. So first one is I, second one is pb, which is 0, and same thing will hold to the other pb whole square, which is again 0, and every other terms are also 0, right? So I am getting identity matrix. So this is the correct answer. Okay, so this is our question number 4. Now 5. Sorry, this is question number 2, 3. This is 4. So here t squared satisfy the property t squared is t minus I. So what can be said about eigenvalues?
But T is invertible.
Okay, yes, it is right. So we know that eigenvalue satisfy the same matrix equation. That is same whatever equation is satisfied by linear transformation, eigenvalue will also satisfy the same polynomial.
Yes, sir.
This is easy to check, right? Cit to the power I, this is 0. That implies if we apply on eigenvectors, we'll get Ci lambda to the power I times that eigenvector is 0. But eigenvector is non-zero. Therefore, that is 0, right? So if lambda is an eigenvalue,
Sir, D is also correct.
yes, then lambda square minus lambda plus 1, that will be 0, because this equation is t square minus t plus I is 0.
Correct, sir.
So lambda, what if we solve?
Minus omega square will be the rules.
Yes, it is 1 plus minus root over b square minus 4ac, that is
1
root
plus
3i.
root 3I.
So that means eigenvalues eigenvalues belongs to this set. It is either uh, yes, belongs to this set 1 plus minus root 3 I by 2. Therefore, it is clear that lambda cannot be 0. Hence, t is invertible. Right?
Sir, n also cannot be, sir, odd.
N?
N cannot be also odd.
Yes, because eigenvalues will appear pairwise. So, n
Yes, sir.
cannot be odd. That is a good observation. So, what is the possibility of eigenvalue being 1? So, it is clear that lambda is not 1.
Uh, Possible
Therefore,
eigenvalues are given by, sir, this.
yes. So, if we assume t minus I invertible, then what is the conclusion? If we assume t minus I is invertible, that will imply, uh, sorry, t minus I is not invertible. If we assume that, that will imply t
Zero is
minus,
eigenvalue of the this.
yes, there exists some v such that t minus iv
One is
equal
an
to,
eigenvalue, sir,
yes,
of t.
tv equal to 1v. That will imply 1 is
One
an
is an
eigenvalue,
correct.
which is a contradiction. So, contrary. Therefore, contrary. Therefore, t minus I is not invertible. This is for B. This is for A. Lambda is non-zero. Therefore, by the same reason, t is invertible. This fact is already known. That is, if eigenvalue is 0, if and only if that is not invertible. Now, t has a real eigenvalue
Not true.
because t eigenvalues belongs to this set, so this is false. Now, what about the last one?
This is correct.
Yes. So we can see the last one because t square minus t. So t square is t minus I. So what about t cube? T cube is t square times t, but t square is t minus I. So t minus I times t, and this is again t square minus t, but t square is again t minus I. So it will cancel. So we will get minus I. So D is correct. Okay. Now, what about this question that
With only one eigenvalue.
yes, 1 is the only eigenvalue.
Sir, option A need not be, sir, true.
Hmm. So, what is the characteristic polynomial?
X minus 1 to the power the n.
Yes, 1 is the only eigenvalue. So, n by n matrix, therefore x minus 1 to the power n. Right? Because dimension is given as n.
E and D are correct.
Now, Cayley-Hamilton, if we use Cayley-Hamilton, Cayley-Hamilton will imply t minus I to the power n equal to 0. So, C is correct. Now this will again imply t minus I multiplying twice will also give 0. So that D is also correct. CD is correct. Now what about B and A?
Sir, B and A, we can take a matrix, sir, whose diagonal entries are 1, 1, 1, as upper triangular matrix, sir, whose
Yes.
diagonal entries are 1, 1, and
So
other.
we can take this Jordan form, right? For example, let us take this 0 and put 1 above those things. So from here it is clear that
So then eigenvalues will not be 1, sir.
yes,
0.
though t to the power n equal to 0, because largest Jordan block is n by n. Therefore t to the power n will be 0, but t to the power n minus 1 cannot be 0. It is easy to observe, right? So this is non-zero, and hence t is also non-zero, because t to the power n minus, if t is 0, then t to the power, you can see that t is non-zero. It is, so those are false.
Sir,
Yes.
sir, I am unable to understand this.
Which thing?
The example you have given, sir.
Okay.
Sir,
So I
t has, sir, 1 as eigenvalue. Sir, you are taking t this. So 0
oh
is the
sorry about that. Those eigenvalues are 1. I have taken the wrong thing. So diagonal will be 1 1. That is, diagonal entries are 1. Everything in is 1, and just put 1 above the diagonal entries.
So, sir, this will work for option A. This will not work for B. So we have to take, sir, 1 1 1 in below diagonal, sir. But in that case,
No, no, this will also work for option B, because this is the
t to the power n will be 0 in that case.
t to the power t minus I to the power
T minus I to the power n will be 0, but t minus I to the power n minus will not be 0.
yes. So though this is 0, but t minus I to the power n minus 1 is not.
So this will not imply, sir.
It will not imply, but
But
because Jordan form, we know that those Jordan block will satisfy this property. That is, the size of the Jordan block will give the property that to the power n is 0, the size, but if we take the lower degree, Jordan block will not be 0.
yes, sir.
That power will be non-zero. Okay. Now fx is minimal polynomial. It is minimal polynomial of A. Now what about the rank of the matrix Fa? By definition, Fa is 0, right?
Yes, sir.
F is minimal polynomial, then if
0
we, yes,
times 0.
minimal polynomial, that means minimal polynomial is the lowest degree polynomial, such that the
It
matrix,
is the
yes, if
matrix
we put the matrix, that becomes 0. So Fa is 0 matrix, therefore what is the rank of 0 matrix?
0.
Yes, rank of Fa is 0. Yes, so here t to the power n, that is 0, it is given. Now T has n distinct eigenvalues. Can we conclude that?
No, sir. It is n distinct eigenvalues. Sir. It has only 0 eigenvalues, sir,
Yes.
with multiplicity.
So first of all, it is clear that all eigenvalues, if lambda, so if uh, lambda be an eigenvalue, then lambda must be 0. All eigenvalues are 0. Those are nilpotent matrix, and we
Sir,
again,
B and C are correct.
yes, again eigenvalues satisfy the same equation. Therefore, lambda to the power n equal to 0. Therefore, all eigenvalues lambda are 0. So So 0 is an eigenvalue, this is clear. T is similar to diagonal matrix. Is it true? So if T is similar to diagonal matrix, that means T inverse TB T, that is 0. Because the diagonalizable means all diagonal entries are eigenvalues. So eigenvalues are 0, therefore the diagonal matrix will be 0 itself. But that will imply T, representation of T will be 0. P0 P inverse, which is 0. But we can choose something non-zero, right? So T is similar to diagonal matrix, this is false. For example, if we can choose this matrix, take, so C is correct from here, take TB equal to everything is 0 and just above the diagonal put 1. So we can see that this TB, this matrix T is not diagonal. That is, T cannot be similar to diagonal matrix. Whatever we take, P inverse T, TBP, that will always be that is not a diagonal matrix. Otherwise, this will be 0, which is not possible because rank of those two things are different.
Yes, sir.
So D is wrong. Now, what about B?
B is correct.
Yes. So only 0 is the eigenvalue. Therefore, what will be the algebraic multiplicity of 0? That must be n, because characteristic polynomial will be x minus 0 to the power n. So B is correct. T has n distinct eigenvalue is certainly false. Same thing, here n cube is given as 0. Now, what about n? So n cube is 0 means, so we have seen that n is given non-zero, therefore n cannot be a diagonal matrix. N cannot be similar to diagonal matrix. We have earlier seen that will imply n should be 0, which is a contradiction. P inverse np equal to 0, if we assume that, that will imply n equal to 0. But it is given that n non-zero, which is a contradiction. So B is false. A is false. N is similar to diagonal matrix. Sorry, this is called not similar, so this is correct. B is false.
N is not similar to diagonal matrix.
Yes.
N be a 3 cross 3 non-zero. Okay, sir.
It is
N
clear,
not
right?
non-zero eigenvector. This is
So,
correct, sir.
yes. N has one non-zero eigenvector.
B is not correct.
It is clear because
0 is
eigenvector is always non-zero. That is,
yes, sir.
no. So corresponding to 0, there will be eigenvector, and eigenvector is certainly non-zero. So C
Right.
is
D is not correct because this will imply the N is diagonalizable.
N has three linearly independent eigenvector. If this is true, then we are getting that geometric multiplicity is 3. If if we assume D is true, that will imply geometric multiplicity of 0 is 3, because we are getting 3 linearly independent eigenvector that imply that n is diagonalizable, which is a contradiction. So D is false. Question number 9. Here you can see that omega is a complex number, that is, omega is cube root of unity. Now, what about rank of A? So, if we apply the row reduction, just multiply, that is, apply this operation R2 minus omega R1. So if we do this operation, then omega cube is 0. So this is omega minus omega 0, omega square minus omega square is 0, 1 minus omega to the power 4. Omega cube, 1 minus omega cube is also 0.
Huh?
Yes.
Yes, sir.
So rank of A is certainly 2 because those two are linearly independent.
Yes, sir. Yes, sir.
Because if you multiply omega squared, this is omega squared, this is omega cube, which is not 1. So this
Correct, sir.
cannot be multiple of the first two. So those two are independent. So rank of A is 2. So rank is 2, that implies nullity is 1. Nullity is 1 means 0 is an eigenvalue. This is true. A is not invertible because nullity is 1, therefore A is not invertible. Not invertible, this will also imply A is not invertible. There exists linearly independent vector VW such that
Not correct, sir.
yes, D will contradict nullity equal to 1. Nullity 1, that means there exists only one linearly independent eigenvector.
But we need to check zero. Zero is not only this one.
Yes.
But zero is an eigenvalue, sir. We need to check that zero is the only eigenvalue.
0 is an eigenvalue, it is clear because nullity is 1. That means what is the meaning of that? That means there exists some non-zero vector V such that there is
Yes, sir. Correct. Correct.
solution space of A has
Yes.
rank 1. That is, there exists rank 1, that is V such that A times V equal to 0.
The geometric multiplicity of zero is actually the nullity of the matrix.
Yes, exactly. Geometric multiplicity of given matrix is exactly same as nullity of that matrix. Geometric multiplicity of 0. Yes. So here J is 3 by 3 matrix having all those entries are 1. So J is 1, 1, 1. This is actually wrong. Not for all non-zero x. Okay. So 0 and 3 are the only eigenvalues. Is it clear that 0 is an eigenvalue?
0 and 3 are the only eigenvalues of A. Yes, sir. Correct.
Yes. So rank of J is
1.
1. Therefore nullity of J is 2. Therefore
0 is eigenvalue.
geometric multiplicity of 0 is 2.
Yes.
So there can be only one different eigenvalue. There is exactly one different eigenvalue. So therefore 0 is this. Those two are eigenvalue. Now we need to fill up this set. Those are eigenvalues.
3.
So trace of J is 3, which is sum of eigenvalues. So sum of eigenvalues 3. That means those two are 0. So another eigenvalue 0 plus lambda is 3. So lambda must be 3. So 0, 3 are the only eigenvector. This eigenvalues is 2. J is diagonalizable. Is it true?
J is diagonalizable. Is it true?
Because geometric multiplicity of
Yes, sir,
0.
it is true.
Yes. So what will be the characteristic polynomial? Characteristic polynomial of
X is cube minus 3x square.
yes. It will be x minus 1 x minus 3 times x square, because it must be of degree 3. So other eigen, so it is clear from this set. Therefore, geometric multiplicity of 3 and so geometric multiplicity and algebraic multiplicity are same for all those eigenvalues. For
Yes, sir.
0 and for 3 both. Hence J is diagonalized. Geometric multiplicity of any lambda is algebraic multiplicity of lambda for all lambda. So this is clear. Now what about option B?
B is correct, sir. D is not correct.
D is not correct. Why?
The D is not correct because 0 is sir eigenvalue. So
Yes, exactly. So take this element 1 minus, take this eigenvalue. So take x equal to this eigenvector 1 minus 1 0. So for this jx comma x, this inner product is, so that is should be the correct symbol. So jx comma x, this inner product is 0. Is it clear? Because this is the eigenvector corresponding to 0. So jx times x, though x is non-zero, we are getting jx times x is 0, which is not strictly greater than 0. So D is wrong. Is false. Now what about B?
B is correct.
B is correct because we can see, let x equal to x1, x2, x3, then the inner product jx. So what will be jx? Jx will be that combination of those columns, that is x1 plus x2 plus x3, x1 plus x2 times x3 plus x3. Similarly, x1 plus, just multiply. It will be this column times inner product with x1, x2, x3. So this inner product is clearly, first one is, if you take x1 plus x2 plus x3 common, this is taking inner product with 1, 1, 1 and x1, x2, x3. But this inner product is also x1 plus x2 plus x3. So we are getting x1 plus x2 plus x3 whole square, which is clearly greater or equal to 0 because those entries are 1. That is, we are considering over real thing. So everything is real considered. X is real, that is considered. So this is clear. This is true. Okay. So that is 10. This is question number 11. Okay. It is given that B is same as I plus I. Right? Now we need to prove so I is the identity matrix and A is also real symmetric matrix. So what do we know about real symmetric matrix?
Sir, option D is correct.
Okay, let us see.
The real symmetric matrices has all eigenvalues real.
Yes, all eigenvalues are real.
Yes, sir.
This is one of the important property. And another property is it is always diagonalizable
Yes, sir.
over any field, means over real as well as, means if it is instead of real symmetry, if it is Hermitian, that is also diagonalizable. So it is diagonalizable over R. This is an important property. It will always it
The
may,
real symmetric matrix means all entries are from real and it is symmetric.
yes, it is symmetric matrix means A transpose is A and all entries are.
Yes, sir.
So first one is B. So what will be eigenvalue? So suppose let lambda 1 up to lambda n, those are eigenvalues of A. Then what will be eigenvalues of I?
I
It will be I lambda 1 up to I lambda n, right? Those will be eigenvalues of I times.
yes, sir.
Now this is a polynomial of A. It is,
Lambda 1 plus I,
yes. So
1 plus I lambda 1,
yeah.
comma 1 plus I, yes.
So we know that eigenvalue of I identity, those are actually one, everything are one, right? Therefore, eigenvalue of I plus IA, it will be 1 plus I lambda 1 up to 1 plus I lambda. Those are eigenvalue of I plus I. It is it actually comes directly. It can be written like this because we already know that sum of Ci to the power I, it has eigenvalue of this form Ci lambda to the power I. We already know this fact that
Yes,
any
sir.
polynomial of a given matrix, it has the same eigenvalue of the form of that given polynomial.
Yes, sir.
So from here it is clear that all eigenvalues are non-zero because 1 plus I lambda 1 can never be 0. If you even take lambda 1 equal to 0, because lambda 1 up to lambda n, those are real. Those are real things. So whatever you choose, whatever real entry lambda 1 up to lambda 1 n you choose, this 1 plus I lambda j, those are non-zero. Those are non-zero because of this. So that imply minus lambda I, sorry b, that that will imply b is diagonalizable. Sorry, b is invertible because 0 is not an eigenvalue, right? 0 is not an eigenvalue. Those are eigenvalue of I. Similarly, eigenvalue of I plus I. So b is necessarily invertible. This is true. Now, what about b minus I? Is it invertible?
P minus I is always invertible, sir.
It may not be true.
It may not be true, sir, because, sir,
Take
A
a
has
equal to
zero
0.
eigenvalues.
Yeah. Take a equal to 0. Then what will be b minus I? B minus I
Zero,
is I
sir.
times, which is, so b minus I may not be invertible. So C
Yes,
is wrong.
yes.
Now what about so B is correct, C is wrong. Now what about AB?
AB or not correct, sir.
So it is already clear though B is always invertible, but A may not be invertible. So A must be wrong. All eigenvalues of B are necessarily real. It may not hold, right? If you take this entry, for example, take A equal to identity, then what will be the eigenvalue of I plus I? Those are 1
I
plus
plus I lambda. 1 lambda 2.
lambda 1, right?
Okay, you have taken I. Okay, sir. Correct.
So all are 1 plus I.
Yes, sir.
So which are imaginary, means those are complex, not real. So this is wrong. Okay, up to this everything is done. Let us solve the previous day's singular value decomposition problem. Okay. So what is
Which one book you have taken, sir?
actually that singular value decomposition, that is already you can see those things in uh, Peter Lax or Peter Lay. What is the author's name? That book. Okay, what is that book names?
So you can type in chat box.
Yes. Seeley. You can also look at in that Gilbert Strand book. Gilbert Gilbert Strand. Gilbert. Sorry. Strand or Seeley. Those books actually contains this singular value decomposition. So what is the motivation of this thing? Actually, we know that for real symmetric matrix, as we have already seen, if A is real symmetric, then it is always diagonalizing. So we know that it means A is diagonalizing. So in other words, A can be written as some PDP inverse. Right. Let me look at the given question. Yes. A can be written like this, where D is a diagonal matrix. So another word, moreover, those eigenvector, those will be, you can choose the eigenvector as orthonormal basis. Those are perpendicular, right? Eigenvector are perpendicular, so you can choose orthonormal basis.
Yes, sir.
With respect to distinct eigenvectors, those eigenvalues, those are orthogonal, but you can choose the whole eigenvector set as orthogonal basis, and you can also normalize those things. So this is actually moreover those P is orthogonal matrix because eigenvectors are orthogonal. Therefore, if you form a matrix with those eigenvectors as columns, then that will be orthogonal matrix, which will imply P inverse is P inverse is P transpose, not star. So we can write this as PD P transpose. Now the question is, can we do the same thing for if symmetry is not present? So suppose now A is real matrix, but there is no symmetry, and this is not a square matrix. Previously it was n by n matrix, now it is any n by n matrix. Can we do the same thing? So answer is we can do similar kind of thing. So again the answer is it is true up to some changes. So now A can be written as UD times V transpose. U now it is not diagonal, so we write the name. We give the name sigma and V transpose. Okay. So what will be the U is now m by n matrix. Now what will be sigma? Sigma is clearly m by n matrix, and V is V transpose. That should be n by n matrix. Is it
U
clear?
is M by M matrix.
Yes.
U is M by M and sigma is M cross. Okay, sir. Sigma is a matrix you have written.
Yes. So
I thought that sigma
sigma
is.
is rectangular diagonal. Rectangular diagonal matrix. What is the meaning of that? It means it is diagonal. For example, 2 by 3. Consider this 2 by 3 matrix. Then diagonal entries will be like this 2, or maybe some D1, some D2, but other things are 0. Okay? Or if you take 3 by 2 matrix, this will look like D1, then D2, D1 0 0 0, D2 0, and there is nothing. So those are some examples of rectangular diagonal matrix.
Sir, we shift this diagonal to the above.
Can we shift which diagonal?
D1, D2 in the 2 cross 3 matrix. Can we shift this diagonal one upper? Let's
This
say yes, sir. D1, D2 in.
no, it should be in ascending order. So first one will be D1, then D2, like this. Those are called rectangular
Okay,
diagonal.
so we have to, sir, start from the first entry.
Yes, it will be written successively in that order. First
So,
one, then. So we will need to find those U sigma V. Okay. So those diagonal entries, those are will be called singular values. Diagonal entries in sigma is called singular. Not necessarily symmetric. So let us solve the previous set's problem. Is okay. Yes, that is the previous question, right? We need to solve this problem. A is given 3 2 2 2 3 minus 2. 3 2 2 2 3 minus 2. We need to find those uh, this decomposition use sigma V transpose. So we can apply this. So the method will be like this. So first we take A transpose A. So what is A transpose A? Find singular value decomposition of A. Okay. What is A transpose A? It will be 3, 2, 2, 3, 2 minus 2 times 3, 2, 2, 2, 3 minus 2. So A transpose A, it will look like 13, 12, 2, 12, 13 minus 2, 2 minus 2, 0. An interesting property is that uh, all eigenvalues of A transpose A, those are actually greater or equal to 0, are non-negative real.
Yes, sir.
Can you see this fact? Because proof the proof is also small. If you take V is an eigenvalue, then A transpose AV equal to lambda V, but that will imply V A transpose AV, sorry, V transpose this is lambda V transpose V, right?
But V transpose V is greater than or equal to 0.
Yes. So this is actually AV transpose times AV lambda V transpose V. But AV transpose AV means it is inner product of AV with itself, right? By definition. So left one is norm of AV square, right one is also norm V square. Therefore, it is clear both are it is clear that lambda is norm AV square by norm V square, and norm V square is non-zero. So it is clear that it is always real and it is greater equal to 0 because norm is always non-negative. So this is an important and interesting observation. Now let us see what can be done. So we need to find eigenvalues of A transpose A. To find eigenvalues of A transpose A. So usual process, we subtract lambda from the diagonal and everything else are unchanged. So determinant of this thing is 0. That will imply. So you can also see that 0 will be an eigenvalue, right? It is also, you can easily see, because this is 3 by 2 matrix. So rank of A is always less equal to 2. Therefore, rank of A transpose A, this is also less equal to 2. Rank of AB less equal to rank A, rank B, right? From here, it is clear that so rank is always less equal to 2.
Sir,
Yes.
sir, instead of finding, sir, eigenvalues of A transpose A, we should find eigenvalues of A transpose. Because
Eigenvalues.
in that case, we have to find, sir,
Yes.
the eigenvalues of 2 cross 2. And that would.
Yes. What you are saying is a better approach. So let us find eigenvalues of A transpose, right? Because we know that A transpose A, that is the important fact. Yes, whatever idea you are suggesting is, it is better. We know AB and BA have
Same non-zero eigenvalues.
same non-zero eigenvalues. So it is also clear that A transpose A has an eigenvalue 0. Eigenvalue 0. Since the fact rank of A transpose A less equal to rank of A, which is 2. Therefore, A transpose, their nullity will be present. Nullity will be greater or equal to 1. That is 0 is an eigenvalue. So let us find eigenvalue of BA. So what is BA BA means A transpose, right? So A transpose means it is 3 2 2 2 3 minus 2 and 3 2 2 3 2 minus 2. So from here it is clear that 9 and other are 25. This is 25. Then 3 times 2 6 6 12 minus 4 8. It will be symmetric. So up to this everything is okay. Now can you say what are the eigenvalues of A transpose? Eigenvalues. Determinant of this thing is 0. So 25 minus lambda whole square minus 64 equal to 0. Lambda square minus 50 lambda plus 625 minus 64 is 0. But this is actually equal to 165.
561.
Yes. So maybe a better will be like this. I am unnecessarily making more difficult. 25 minus lambda
88 square, sir.
is square root of 64
Yes, sir.
plus minus 8. So lambda is 25 plus 8, that is 33, and another one will be 24. So maybe I am making some mistake because it should not be like this. So again 3 2 2 2 3 minus 2 3 2 2 2 3 minus 2. So 9 4 4. Oh, 9 8 17. It will be 17. 9 4 4.
33 and 17.
17. Okay. Those are actually 17. Okay, 17 is plus minus 8. Therefore, lambda is either 25
Or 9.
or
9.
9. Okay. So, therefore, from here it is also clear that eigenvalues of A transpose A, those are, if we write in descending order, that will be 25, 9 and 0. Because 0 is already there. 0 is also eigenvalue we have earlier observed. Right? So those two have same eigenvalue except 0. So 0 will be 0. Therefore, what will be the singular value? Singular values will be square root of those things. So square root 25, square root of 9 and square root of 0. Right? Therefore, which is same as 530. Therefore, sigma it will take this form. Sigma will be 5 0 0 3 0 0. Okay, it is 2 by 3. So we have successfully found sigma. Now we need to find other two things, that is one is phi, another is phi transpose.
Sir, if we have, sir, one, sir, uh, sir, all eigenvalues are, sir, non-zero, then how can we write sigma?
All eigenvalues of are no.
Non-zero.
one eigenvalue must be 0 because earlier it is m by n matrix. So
Yes, sir. Yes, sir. Yes, sir. Yes.
yes,
Correct.
because rank will be less equal to,
Yes, sir.
those are not same, therefore at least
One value will be always 0.
if that is n by n matrix, if you start with n by n matrix, then 0 may not appear,
Yes, sir.
because those case it can happen that that is diagonalizable, that is
Yes, sir.
both
Yes.
are same order. Okay, so to find v,
You
yes,
find
first we will find v and then we will find u. So v, the column of v or phi, those are given by orthonormal basis of that previous eigenvector. Orthonormal basis of A transpose A with respect to that eigenvector, with respect to those eigen values, that is 25, 9, 0.
yes, sir.
So what was A transpose A? Let me copy that thing. So this was A transpose A. Now let us find eigenvector with respect to, so when lambda is 25, what can be seen? So lambda, can you see the combination which gives 0?
Which combination?
Can you find a combination which gives, there is A transpose A minus 25i, that will be same as minus 12, 12, 2, 12 minus 12 minus 2, 2 minus 2, 0. So from here it is clear that if you take this combination 1 plus 1, 0, that will give me 0, right? So this is an eigenvector. So
Yes, sir. Yes,
normally,
correct.
so 1 by root 2 times this is an eigenvector.
Yes, sir.
So corresponding to lambda 1, this is an eigenvector. Because if you multiply this with this, that will give you 0, because combination of those first two, if you add those two columns, that is 0.
Yes,
Now
sir.
corresponding to lambda 2 equal to 9. So A transpose A minus 9. This is 4, 12, 2, 12, 4 minus 2, 2 minus 2, 0. Now what will be eigenvector with respect to this? Can you guess and compare? Can you guess? Otherwise we need to solve. So which combination will give me 0? If we add those two things, then lower thing is 0, 16 and plus 6. Yes, so it is, oh sorry. We need to solve, maybe we let us solve this thing. So if we do the row reduction, so this is rough. If we do the row reduction, this is 4, 12, 2. Then maybe let us start with the last thing. Easy to work with the last one. So 2 minus 2, 0. So subtract 4. That will be 0. Plus 4, that is 16. This is 2. Now 12 minus 12, which is 0. So multiply 6. So we are doing R1 minus 2R2 and 2R3 and R2 minus 6 R3. So plus 12 against 16, and this is minus 2, 0, 0, 0. Now, yes. Now you can also further reduce it. So it will become 0, 16 to 0, 0, and minus 4. Minus 4. So what will be a solution? You can take null space. What will be null space of this?
Sir, x3 will be 0. All are 0.
Sorry, I am doing something wrong. 2 minus, this will also there. 2 minus 2, 0. Sorry. So that is, so we can do half times R3 and we can move it to first row, that is 1 minus 1, 0. Then second one is 0, 16 plus 2, and third one is
0, 32, 0, sir.
0, 0, 4 minus 4. So you can make it 1 by dividing. Now what, something is wrong. That is, oh sorry, I have not subtracted here. So because that's why I am getting 3, that is rank is getting 3. So I have not subtracted from the last diagonal, which is 0 minus 9. So this is 9 minus 9. So now is it clear which combination will work? Okay, maybe let us do it again. Okay, so first one is 4 minus 4, which is 0. Or we can also reduce, we can divide from the first, so it will be 2, 6, 1, and dividing from the second, it will become 6, 2, minus 1, and then it is 2 minus 2, minus 9. Now further
Yes, sir.
subtraction, so let us, this is the row 2. So it is 2,
0
6, 1,
minus 4, 16,
second row
sir.
will become
0
0,
minus 16.
yes, minus 16,
Yes,
and
sir. Minus 4.
R2 minus 3 R1.
Minus 4.
Minus 4, right.
To 0 minus 8. Minus 10.
Minus 8,
Minus 10. Okay. Divided by, sir, 2. Second row.
yes.
Minus 2, in fact.
So if we divide this,
2,
again I am
8,
getting something wrong.
8. Why, sir?
Then is it 1, 2, 6, 1, then 0, if we divide,
8, 2.
yes, 0,
8,
4, 4, 1, and
okay,
6,
sir, 4.
4, 5.
4, 5. Yes, sir.
Now,
Rank is coming out to be, sir. This is an invertible matrix. So,
yes, this
solution will be, sir,
is
0.
invertible because 9 is an
3
eigenvalue.
is an eigenvalue, sir. You are writing.
Yes, what is wrong? Okay, let me again check. 13 minus 9, which is 4, 12, 2. Then 12, 13 minus 2. 12, 4 minus 2. Then 2 minus 2 and minus 9. Maybe I am doing some mistake. calculate it again. So 6, 2 minus 1. 2 minus 2 minus 1. R3 minus 3 R1. R2 minus 3 R1. So this will be 0. Minus 18. 2 minus 18 minus 16. Minus 1 minus 3. Minus 4. Then R3 R3 minus 2 R3 minus R1 minus R1. So it is 0 minus 2 minus 6 minus 8 minus 9 minus 1 minus 10.
Sir, our eigenvalue is correct. 2590.
Eigenvalues are correct. Yes, let me check it again. Maybe eigenvalue I have computed it wrong. Okay, so if we see this A transpose A, yes, yes, eigenvalue must be wrong because if one eigenvalue is 26, 25, then other eigenvalue must be 1, right? So either A transpose A. So let me do it from the first beginning. So what is this 3 2 and 3 2? This is 13. 3 2 means 6 plus 6 12. 6 minus 4 2. Then 2 3 2 3 13. 2 3 2 minus 2. 4 minus 6 minus 2. And what is the last one? 4 minus 4 0. Yes, so one eigenvalue must be 25, another must be 1. If so, there should be some mistake. Three two two and 2 3 minus 2. 3 2 2 2 3 minus 2. First one is 17. 9 and 4 4 8. 17 it is okay. 6 6 12 minus 4 8. It is also okay. So this is also correct. So where is the mistake? So 17 minus lambda whole square minus 64 is 0. So 70 minus lambda, that will be same as plus minus 8. So 70 plus 8 which is 25, 70 minus 8 which is 9. And it is also clear that if we subtract 25, then that will become minus 8 minus 8. So this is eigenvalue, it is clear. If we subtract 9, that will become 8 8. This is also correct. I don't know where is the mistake.
Sir, why you not calculate directly?
Yes,
Using
direct calculation will give us the eigenvalues 0 1 25, because it is also clear, right? 25 uh,
26, sir. Sir, trace is sir 26.
this is 26. That's why if one eigenvalue is 25, then another must be 1. And 25 eigenvalue is 25. This is clear because minus 12. Yes, 12
Why
minus
we are getting sir 9? Where is the mistake?
yes, maybe something is wrong. I don't know where is the mistake. Okay, maybe avoid this thing. I have calculated wrong somewhere. So maybe directly put those eigenvalues. So 25 is eigenvalue. This is not an eigenvalue. Lambda is 2 equal to 1. This will be eigenvalue. Okay. So if we subtract 1, then this will become 12. And this is also 12. This is minus 1. This row reduction will now not work. It will not work. Okay. So what will be V2? Can you find V2? Now maybe it is easier. So let us solve this. Okay. Row reduction.
So you are taking 1 as eigenvalue.
Yes, 1 is eigenvalue. Lambda 2 is 1. Also, we can, let us look. Oh, D is not given. Okay. Row reduction will give me 12, 12, 2, 0, 0, minus 4, and then 2 minus 12, 12, 2 minus 2 minus 1.
Sir, I am getting eigenvalues as a 25, 1 by 2, 1 in bracket 1 plus under root 33, and third one is 1 by 2 in bracket 1 minus under root 33, sir. I'm getting from it, sir, online, sir.
So, what are the eigenvalues of A transpose A?
Sir, are sir 25, 1 by 2 in bracket 1 plus minus under root 33.
No, no, that is not possible. 0 must be eigenvalue, and so that is wrong. Maybe something wrong.
So I think we have calculated sir A transpose is incorrectly, I think.
Yes, A transpose A is correct.
Sorry, sir, A transpose.
Maybe there is some computation issue, but if we start with A transpose A, then it is clear that one eigenvalue is 25, then other must be 1. 25 is an eigenvalue, right? Because we are getting a solution. So another must be 1. So this is A transpose A minus 1 I. So, okay, minus 1. Okay. So if we row reduce, then we are getting this thing, and now reduce it further. So I have done this operation R2 minus R1. Now we can do R1 minus 6 R3, which will give me 0. Yes, 0, 0, 0. Now it is okay. 0, 0 minus 4, 2 minus 2 minus 1. So which combination will, so what is the solution? Solution space. It will be generated by this one, right? What is the free? Free will be third column. So we can choose anything in the third. So third place, if we choose 1, then sorry, third place is not free. Second one is free because this is the pivot column, right? So we can choose anything in the second place. So we will choose 1. If we choose 1, third is definitely 0 because minus 4 times something is 0, that will imply that will be 0 itself. So if we choose second one is 1, that is minus 2, then first one will be also 1. So 1, 1, 0 is the solution.
Sir, for A transpose, A is not correct.
Yes, A transpose A is not correct. What will be that?
So 0, sir, instead of 0, we have to write 8, sir.
Oh, yes, yes, you are right, exactly. That is why everything is
Yes, sir.
wrong again and again. Okay, thanks. Thank you for correcting. That must be 8. So Yes.
So the sir eigenvalues are correct, sir.
Yes, previous was correct 17, so we need to change it, make it 8. Okay. Okay, so lambda 2 must be then 9. Is it 9? Yes, 9.
Yes, sir.
So again we'll compute A transpose A minus 9.
So you need to only change the last entry.
Yes, last entry minus 2. Okay.
So we have, sir, you have to also change lambda one, sir, for calculation of the calculation of lambda corresponding to lambda one will be also changed.
Yes, it is okay. There is no issue because only the last. It is not depending on the last column, so it is okay. Because I have chosen 0 for the last.
But sir, you have to sir, subtract 25, na? Then you will get sir minus 17 there.
Yes, yes. Minus 17, but it will give me the same solution because
Yes, sir, this is
I have
correct.
taken the combination of the first two things.
Yes, sir.
Mm, okay. For 12 2, so row reduction will give me. So we can do
So first divide by sir 4, 2 first.
2 6 1
It's
6
2 minus 1,
minus 1 2 minus 2.
2 minus 1.
Yes.
So it will be sir 2 6 1 0 minus 16 minus 4.
Minus
0 minus 16 minus 4
yes 0 minus 16
minus 4.
minus 4.
0 minus 8 minus 2 minus 2. Yes, sir. Now we'll get. Last one is depending upon, sir, the second row. So last will be 0.
Yes, last row will get cancelled 0 0 0 and
So
above
six
that we
one
can choose 0
0
4 1.
261.
1.
So x3 will be, sir, minus 4x2.
Yes, so
X,
if we say we are not reducing because it will get fraction, so I'm not reducing it
yes,
further, but we can see there are two equations 2x1 plus 6x2 plus
6x2 plus
x3 is
x3.
0 and 4x1 plus 4x2
x2
plus x3
is
equal
0.
to, so we can choose x3 equal to 1. So if we choose x3 equal to 1, then
Minus 4.
or sorry, maybe x2 equal to 1, let us choose that. Then x3 equal
Minus
to
4.
and if
Okay,
we
sir.
put here 6 minus
6
4,
minus
that is
4,
plus
2. Minus 1. Yes.
okay, great. So the solution is minus 1 1 minus 2.
Yes, sir.
We can we just divide it by norm. So what is the norm? 16 1 by root 18, right?
18.
Okay, because square root of 16 plus 1 plus 1, which is
Yes,
18.
sir. Yes, sir. Correct.
Okay, now with respect to lambda equal to 0, lambda 3 equal to 0, what will be that? Then we will get v3 equal to corresponding to 0. It is easy to see, is it? Because we can choose yes, if we subtract, that is c1 minus c2 plus half c3, that is 0, right?
Uh, C3,
1
C1.
1 and that is plus 4.
The minus, sir. Minus 1 by 2 C3.
Yes, minus 1 by 2 c3. So 1 minus 1 minus half.
Correct.
So 1 minus 1 minus half, that will be, that is the eigenvalue. Okay.
We have to divide it by norm.
So we need to divide it by norm. Maybe let us multiply with 2. So 2 minus 2 minus 1. So what is the norm of this thing? 1/3.
3, 1 by 3.
So those are uh, orthonormal eigenvectors.
Vectors, eigenvectors.
So yes, therefore V will take this form. Is so first one is 110, 1 by root 2, 1 by root 2, 0. Second one is
1 by root 18 minus 1 by root 18, 1 by root 18 minus 4 by root 18.
minus 4 by root 18. The last
2,
one is
1
third.
by 3 plus 4.
So we have computed V, right?
Yes.
Now we need to find uh,
U.
U. Okay. Okay, great. Let us find U. Yes. So the first U will be 2 by 2 matrix, right? So to find U. So the first column will be it will be of this form, sigma 1 inverse A times V1. So that is V is actually V1, V2, V3. That is actually V. Now what is sigma 1 inverse? So that this is sigma 1, sigma 2, this is sigma 3. Sigma 1 means 5. So sigma 1 inverse means 1 by 5 A times V1. What was A? Initially A was this matrix. A times V1, right? V1 means it is 1 by root 2, 1 by root 2, 0. So we need to add first two columns. That is 5, 5 and 1 by 5 root 2. That is 1 by root 2, 1 by root 2. So first column is
Sigma 1 is, sir, eigenvalue of A.
no. Sigma
What?
1 is square root of eigenvalues of A transpose.
Okay, sir, okay.
Singular values. Now same second column. This is sigma 2 inverse A V2. Second eigenvalue was second singular value was 3.
That's 1 by 3,
Yes.
3, 2,
Now what
2,
is V2?
minus 1 by root 18, 1 by root 18, minus 4 by root 18.
Yes. V2 was that minus 1 plus 1 minus 4. 3 2 2 3 2 minus 2 and
Minus 1 by root 18,
into minus 1 plus 1.
minus 4.
Okay, if we multiply this, what will happen? 1 by 3 root 18, and then we'll get
Minus 3 plus 2 minus 1, minus 9.
minus 9. Yes, right? And
Minus 2
2
plus
plus
3,
3 minus
1 plus 8, 9.
plus 1 plus 8 plus 9. Therefore, you will take this form. So it
So
again,
9 will be 1 by root 3 minus 1, 1.
yes, 1 by root 2, 1
3,
by
sir. Root 2, sorry.
yes. So you will be of this form. First column is 1 by root 2, 1 by root 2. Second column is minus 1 by root 2. 1 by root 2. So it is done. So which of the following is correct? First one is
So
this.
U,
This is okay.
Yes,
This
sir.
is okay. Now what is phi? Let us compare phi.
Yes, sir. We have to take transpose, sir.
Oh, wait, I have computed phi transpose.
UDV transpose.
U sigma phi transpose. Yes, I have already computed phi. There is no issue.
You have computed V, but you have to take transpose.
No, no, it is okay. Uh, I have computed. Yes, yes. I need to take transpose of that thing. Yes,
Sir, where you have
I
to
have computed the decomposition actually. I have computed phi transpose. Right.
where you have computed sir transpose? You have only sir, found V. Sir, in the computation process, we have to take the transpose of V.
Yes, I have to take transpose of that. So comparing with this, uh,
Sir, it is not matching with anyone's.
it is not matching. 1 by root 2 minus 1 by root 18.
But it is written in sir we do not need to take transpose sir.
Mm-hmm.
But no answer is sir matching. But
Just
what?
let's see what is matrix whose columns are v1 of the v.
Sir, maybe I think they are putting these values in a row. I think you have you are taking in columns as a column vectors. I can.
Yes, yes. That's why transpose is needed. It is okay. But after that, answer should match, right? After that, there is no mistake. So this color, this matching, this those two are wrong. Therefore, this should be the answer. 2/3 minus 2/3 minus 1/3. Only the third row is there is a sign issue with the third. Okay, there is no issue actually.
There is no issue, sir. We can take minus.
Yes, we can if we start with negative that
Yes, sir. Yes.
this will give me
So in that case, this is true fit. No, sir.
yes. Then we are getting option B.
B. So take sir 1 by root 18, 1 by minus 1 by root 18, 4 by root 18. Sir, the but thing is how they are putting eigenvectors to form the sir matrix V. Are they putting as column vectors or considering like row vectors?
Just let me check that thing. Just let me check singular to Yes, it is okay. He should be that column. There is no issue. My computation is okay. It is maybe that it is given as V transpose. That V transpose is given. What was the answer? Option B is correct actually, according to the answer key. There is a sign issue. Maybe let us look at.
Sir, you can take 1 by root 18 minus times then sir 4 by root 18. Because if sir alpha v is an eigenvalue, then minus alpha times v is also an eigenvalue.
Yes, yes. We can choose the negative minus V also.
Yes.
Yes, you're right. So we can put a negative sign here. There is no issue. Right. Okay. So, but the fact is that he, whatever I have constructed, that should give the desired V actually.
Yes, sir. We do not need to take transpose.
Maybe there is some mistake. That is, transpose is given actually.
Yes, sir. It may be.
Because I have looked at the example, look at the procedure. We don't take the transpose. Is V will be formed by those eigenvector.
Yes, sir. Because we need a 3 cross 3 matrix, na?
Yes.
So we calculate A transpose A.
Yes. So it is okay that whatever I have written, that is correct. Yes. So that is the answer, final answer. There should be transpose need to be added here. Okay. Then option B will be correct. Okay. Sorry for lots of mistake in this question. And I have not actually earlier. I have not used singular value decomposition anywhere. That's my first composition, first calculus.
Yes,
Okay.
sir.
So let me stop here. Thank
Okay,
you.
sir. Thank you, sir. What about the question I have asked you yesterday?
Question?
I have asked one question to you, na, sir, yesterday.
Which which question?
The congruency of two matrices over.
Yes, yes. That is actually not. That is actually not very obvious question.
Sir, I have asked it to Sopan sir.
It will depend on the
Yes.
field.
Sir, you can both discuss on this issue, sir.
Okay, okay.
Yes, sir. I have asked him also. Sir, it was not also immediate